Section 7.3 is the shell method, or sometimes you'll hear it called cylindrical shells. We'll talk more about that when we get to that method, when we get to the videos where it shows that method. The basic idea is that when we worked with the disk and the washer methods, we saw that our rectangular regions were perpendicular to the axis of revolution. You guys remember that, right? Always a perpendicular. And when our region was spun, it created a disk or washer. In the shell method, our rectangular region is parallel to the axis of revolution. And when our region is spun, we create a cylinder. The pictures in the videos will give you some, concrete picture of what this is doing. But one of the ways that you could remember which one's which is the disk and the washer is the perpendicular. The shell is parallel because it rhymes. So mnemonic devices are very helpful for me. I don't know if they are for you, but shell and parallel rhyme. So the shell method's the one that's parallel, the other one's the perpendicular. Okay. Obviously that means that your picture looks a little different when you create it. So you have to be very careful when you're creating your picture that you do in fact get that parallel rectangular region and not a perpendicular one when we're doing this method, especially on the tail ends of doing the other one. Okay, so what we're going to do next is we're going to watch 3 YouTube videos about cylindrical shells so that you can kind of grasp what you're doing differently in terms of a 3-dimensional object with this method. Okay, y'all ready? Let's do it. So we took a look at some videos that kind of developed for us why there is a need, really, for another method. That was his last example. He talked about why the washer method would not work very well and how it complicates things with the curve sine x for the integral limits that he gave you. And as he did this, he came up with and created with you talked about the volume of the cylinder, and he talked about the volume of the cylinder being 2 pi times the radius times the height times the thickness. And then we talked about letting this be infinitely thin, right? Letting the thickness approach 0. And if we do that, we end up with 2 different, although very similar, equations for volume. One of the volume equations is because it's on the horizontal axis, and the other one is on the vertical axis. You'll notice that the formulas are the same. It's the radius times the height times dx or dy. And the limits of integration correspond to whether you're in the x limits of integration or into the y limits of integration. So again, just like with the washers and the discs, what I'm going to request that you do and ask, not request is like a nice way of saying require, okay? What I'm going to request that you do is that you draw the rectangle that we're spinning, okay? If you are artistically inclined and you want to draw me a picture of the 3-dimensional, you can do that. If it helps you to visualize that, that's great. You don't have to, but what I would like to see is the representative rectangle region, okay? So that's what I'm going to show you how to draw and how to use that diagram to make the identification of the radius, the height, and the thickness, and then identify your limits of integration, and then we'll integrate. Okay, you guys ready to try one? Sure. We haven't actually seen one finished, right? We've only seen one started at this point. So we're going to use the shell method to evaluate the integral that gives the volume of the solid generated by revolving y equals 4x minus x squared, x equals 0, and y equals 4 about the y-axis. So you're welcome to grab your calculator to get an overall picture of this. This is a parabola, correct? Yeah, 4x minus x squared. Opening how? Downward, because the negative is on the, or the x squared has the negative in front of it. And we have x equals 0. What is another name for the line x equals 0? The y-axis. So we're looking at the y-axis. And we're looking at y equal 4. So those are our limits of integration that we have to work with. Not limits of integration, but limits of our boundary. So as you take a look at this, here is an axis for us. The graph 4x minus x squared is a parabola opening downward, and it looks, let me try that again. It looks roughly like this. Okay? We're not real interested in being super specific, but a sketch will do.
Why is it to the right?
Why is it to the right? Because if you were to take the negative out, you would get 4, you would have x minus 4, and it shifts it so that it has an x-intercept at 4. So we actually have x-intercepts at 0 and 4 here. So not that we necessarily will need it, but they do go from 0 to 4. It's also symmetric, so we may need this as well. This has actually got a maximum at 2. Our y-axis was what we mentioned as being a useful boundary, or a specified boundary. And the other one that they specify is the line y equals 4. And y equal 4 actually hits my graph right here at that maximum value, if I drew it well. I did not draw it well, so let me try one more time. That's not too bad. So if we are looking at the area, and it said we're spinning about the y-axis, okay? So we're spinning this piece right here. So if we look at the area trapped between those 3 curves, the area that we're looking at is this piece right here. Can you all imagine that? And if we were spinning that, we would get something that looks kind of like a funnel. It would be filled in though, right? It wouldn't allow us to actually pour something in it, but it would be a filled in funnel. Okay, everybody good so far? All right, what we need to do inside of that blue region is we need to draw a representative rectangle. Now, the representative rectangle has to be parallel or perpendicular to the axis of rotation. Parallel. Using the shell method, we're going to draw a parallel rectangle. So our axis of rotation is actually a vertical axis of rotation, so my rectangle will also be vertical, like this. Okay, so that's one side of a cylindrical shell. That's what I actually drew in. One thickness, one side of that cylindrical shell. And you can imagine, and you don't have to draw this, but you can imagine the other side then, of course, is over here. And then they're connected like this, right? So there's that shell without the other half of my figure drawn. So in terms of this shell, we have 2 pieces that we have to identify. We have to identify the radius of the shell, and we have to identify the height of the shell. Okay, and it's based in part upon the axis of revolution and in part upon the equation that we're looking at, and then in part upon the region that we're shaded in, like the part that we're shaded in for our region. All right, so we're looking for a radius and for a height. So our volume is 2 pi. Remember, that comes from the fact that we're dealing with a cylinder, volume of a cylinder, times the integral. And we're going to be looking for the radius, and we're going to be looking for the height. Now, as we take a look for the radius and the height, it's important to notice which of the limits of integration I'm going to use. And that's based on the thickness that we see here. So is this thickness going to be delta x or delta y? It's delta x, so we're going to be using dx. So all of our limits of integration, or all of our components inside of our integral, are going to be in terms of x. Right? And if we need to write it in terms of y for a moment, and that's okay, and then we can change it into the terms of x when we're actually starting to integrate, okay? But eventually we need this all in terms of x. So if we're looking at this in terms of x, we also need our limits of integration, right, the upper and the lower bound on top of our integral, to be in terms of x. So what are the upper and lower limits for our x value? It's 0 to 2. The shaded region goes from 0 on the y-axis all the way over to 2, which is the peak of our parabola. So this goes from 0 to 2. Okay, everybody good so far? Okay, our radius of our shape is this distance right here. Let me just call it r for the moment. What is that radius? It's x. It's just how far I've gone in the x direction. And that's really friendly for this particular one because I'm working in terms of x. So my radius is simply x. So up in our integral, I've got x. The radius was the easy part. Okay. The height. Well, the height is this piece right here. Yes? Okay, so this starts to feel a little bit like what we did in the last section. You've got to figure out what that height is based upon the region that you're working in, right? So if it went from the line that's red at y equal 4 all the way down, it would be 4. It doesn't go all the way down, though. How far down does it go? Tell your equation, right? It goes down to here. So it's this whole distance, 4, and then I have to subtract y, because that's the height of my curve. So in some sense, this is sloppy, but I'm going to write it anyway. This is 4 minus y, because y is the height of the curve itself. So the height of the actual rectangle is 4 minus y. But I need to change that. I cannot really actually integrate this with the x and the y in there. So I have my 2 pi, my integral from 0 to 2 of x times 4 minus, and what is y?
4x minus x squared.
Yeah, it's 4x minus x squared. It's the equation for y equals, and then I have dx on the end.
Where did you get the x? How'd you find r equals x?
Because the point right here, he talked about this, one of the ways of thinking about this in this video is that this point right here on the edge, I need another color. Let me use maybe blue. No, I already used blue. How about green? It's still blue. This point right here is the point xy.
Oh, okay.
Yeah.
Yeah.
So the width is x, the height is y at that particular point. Okay, this is all the hard part, setting it up. We're going to clean it up and we're going to integrate now. So let's try that out. We have distributing a negative, and then we have multiplying through by x. Well, we have subtracting from the 4 and then multiplying through by the x. I'm so sorry. I need to change out my stylus, and I keep forgetting to do so whenever I leave this room. So I have x here, and then I have 4 minus 4x minus x squared. So that would give me 4 minus 4x plus x squared dx, multiplying through by x. I have 4x minus 4x squared plus x cubed dx. We need to integrate. So what is the integral that we're going to get for this?
2x squared minus 4x cubed divided by 3 plus x to the 4th over 4.
Okay, is everybody good with that? We're evaluating at 2 and 0, and we like zeros, right? They're nice to evaluate at. So when I plug in 2, I've got 2 times 2 squared minus 4 times 2 cubed over 3 plus 2 to the 4th, oops, over 4. And all of that is actually minus 0, because plugging in 0 gives me nothing since it's a polynomial. So when I plug all of that in, simplify with algebra, and I left off something at the beginning, the 2 pi. So don't multiply the pi through. Our answer will be in terms of pi, but you can multiply the 2 through when you're done. Did you guys get a value?
I got 8 over 3 pi.
That's exactly what I have, Abby. Good job. 8 pi over 3. And it makes sense that pi would be involved, right? I'm working with cylinder. Right? Cylinder has a radius and so forth, and we're doing a circular kind of region. Any question on that one? Evan, you look confused. Are you okay? Try another one. Okay. Sure. All right, the directions are all the same. My regions have changed, so all three of my problems have the same directions on this set. We're working with the line y equal, not the line, excuse me, the curve y equals x cubed, and then the lines x equals 0, y equal 8, and then we're working with the x-axis on this one, okay? So we're setting up this different integral, and we're revolving around a different axis. Okay, so y equal x cubed, you guys know what that looks like. It looks something like this. I didn't draw that well because I want this to be the port. This looks something like this. I'm using this with x equals 0, which is the which axis? That's the y-axis, so we're bounded by the y-axis, just like before. And with the line y equal 8, which is up here. Just so that we have it sort of scaled in our minds a little bit, how far does that mean I go out on my x-axis? It's 2. Yeah, because 2 cubed would give me 8, right? And my equation is y cubed. So this goes out to 2. And the region is going to be the part that is trapped between those three lines and curves, those three curves, we'll say. So here's my region. And I'm supposed to be rotating now about the x-axis, which is this one. So when I draw my representative rectangle on this one, will it be a horizontal rectangle or vertical rectangle? It'll be horizontal because it needs to be drawn parallel to the horizontal axis, the x-axis. Okay, so I think this might have helped a little bit when Levi asked it, so I'm going to point it out over here. This point right here on the edge in green is my point xy. So it's the point that gets spun around, right? I mean, they're all getting spun around, but if you sort of focus in on one point, sometimes that's helpful. So I've got this piece here. If you want to draw the corresponding piece below, at least to give you some sense of perspective, you've got a piece down here about like this, and you're spinning this like so. So there's my cylinder. Okay, so on this one, am I rotating this, or I'm sorry, am I integrating this with respect to x or y? It's actually y on this one. Do you see the dy? So I've got 2 pi at the beginning. I'm integrating with respect to y, so I'll put dy at the end. What are my limits of integration on y? Yeah, 0 to 8, or 8 down to 0 if you prefer. Okay. All right, radius first. What is the radius? That is, what is this distance for my cylinder? It's y, right? That distance is y. Okay, so that's nice because I'm actually working in terms of y. So my radius is actually y on this one. What is my height? Yeah, it's actually x. I don't have to do anything minus anything, right? I'm actually going from the y-axis all the way over to my curve, and that's my height of my rectangle. So my height, as Caleb said, is actually x. And that's actually accurate, right? I mean, this is an accurate statement. It's just unfortunately got 2 variables in there that we need to substitute for something. So I need to get rid of, in this case, the x, because my limits of integration and my integral are supposed to be working with respect to y this time. So what is x? Yeah, so my equation was y equals x cubed. And if I solve that for x, then x equals the cube root of y. So I'm going to replace my x with cube root of y. All right, so we're not really going to keep those separate though, right? I've got y times the cube root of y. How can I sort of combine those together so that I can integrate them easily? Yeah, I've got y to the 4/3. So if you'll remember, this is y to the 1, and then the cube root of y is y to the 1/3, so this is y to the 4/3. dy. All right, so antiderivative of y to the 4/3. Good, all right. I'm going to use this next screen since I've got the space in here. Okay, so the 2 pi is going to stay. The y to the 4/3 becomes y to the 7/3. And then we would divide by 7/3, or in this case, I might want to write it as multiplication by 3/7. Sorry. We're evaluating at 8 down to 0. Everybody good so far? So I have 6 pi over 7. And this is the cube root of y to the 7th, which I find to be a little bit more helpful in evaluating than the power 1/3. Well, the power 7/3 in this case. The 8, what is the cube root of 8? It's 2. So I do the cube root first because I can make my number smaller. It's 2. And then what is 2 to the 7th? It's 128. So when I plug in the number 8 here, I'm actually going to get 128. I'll write it down to show that I did it. So this is the cube root of 8 to the 7th. I would not do 8 to the 7th. Plugging in 0, of course, gives me 0. Everybody's good with that, right? So this is 6 pi over 7 times 128. And then does 128 divide by 7? No? So we're going to just multiply the 128 by 6 then, and what do we get? 768 pi over 7. Any questions on that one?
Why did you do dy instead of
This one's dy because the height right here is delta y. That's why. Yeah, it's all based on that rectangle's thickness. All right, one more. Same directions. We've got a different curve. In fact, we have 2 curves this time. Y equals x squared and y equal 4x minus x squared, which we saw earlier. And we have the line x equal 4. So this one's a little more complicated simply because we have 2 curves instead of 1 curve and 2 boundary lines. And we have it rotating also around something that's not the x or the y axis, which also creates sort of a different feel to it as we're setting it up. So let's take a look at this function, this function's graph. We drew the curve y equals 4x minus x squared earlier. And you know what the graph of x squared looks like. So if you were to put both of these in the calculator and look at where they're crossing, that's what you would be looking for. And the graph will look something like a leaf. Okay, they will cross in what seems to be a leaf kind of shape. Obviously, one of those coordinates where they're crossing is the origin. It's at 0, 0, right? This other coordinate where they're crossing, with a little bit of algebra or with graphing carefully with your calculator, you can find those limits of integration, or those intersection points. And this is at the point 2, 4. Okay? And we're supposed to be rotating around the line x equals 4, which is a vertical line over here that's, you know, another distance away. It's not connected, I guess is what I want to say. So I've got this line over here at x equal 4 that I'm rotating it around. Like so. The region itself, if I shade it in blue, of course, is this leaf in the middle here. I should have shaded it in green so it really looked like a leaf. That would be better. How am I going to draw my rectangle? Vertical. It's parallel to a vertical line, so it is vertical, like this. And you can imagine, you know, its counterpart is over here, and we're making these really wide cylindrical, or cylinder, right? It's really wide like so. Okay, is everybody good with the basic overall image? We need a radius and we need a height. So the radius is supposed to be right here, correct? How am I going to get that radius? Okay, so this is a distance of 4 away, right? So it'd be 4 minus something. What? Okay, not the second function, but I know why you're saying that. Because the function itself gives you a vertical distance, and I'm talking about a horizontal distance. I need to take away this piece right here, right? What is that squiggly piece width, length, numerical value? Y'all did it earlier. It's x. It's just x. Right? It's just x. So my width is 4, I'm sorry, my radius is 4 minus x. Okay, volume is 2 pi times the integral. Am I doing this with respect to x or y? dx's or dy's in this one? Dx. And the picture is because that's the thickness of the rectangle, it's a width of x, right? Okay, good. And so this is actually going to be in terms of x, which is friendly on the first one because it is 4 minus x. That's my radius. 4 minus x. So the whole length out to the line that's dotted, 4, minus the piece at the beginning, which is my x value of my function. All right, how about the height of my rectangle now? It is a y value.
Is it gonna be 4 minus 1?
No, but you're thinking right. We're going to have to subtract something. Yes, can you describe what you did, Evan?
I subtracted the 4x minus x squared from the x squared.
Okay. All right, so let me rephrase. You subtracted the curve that's on top minus the curve that's on bottom. Does everybody see that? We did that before, right? In 7.1 when we were looking at areas of regions. Remember? We looked at the area of the top. We took the function that was on top minus the function that was on bottom. And the function that's on top happens to be the 4x minus x squared function on this one. Minus, and then the function that's on bottom is the x squared function. So I know I don't really need these parentheses, but I'm going to put them in just to indicate that that's where it came from. So this was the first y value, or actually the second one, and this was the other y value. So this is like y2 minus y1, kind of, right? If this were y2 and this were y1. Okay, we're going to clean that up a little bit. I'm definitely going to multiply it all out before I actually do any integration, because I don't think we really need to do any. Oh, we haven't put that in yet. Thank you very much. What is our integration from? 0 to 2. How do you know it's 0 to 2, K?
That's where it meets on the x-axis.
That's where it, what is?
That's where it meets. On
Yes,
the
that's where our blue region is on the x-axis. Very good. So I've got from 0 here up to 2 here. Thank you for that. Appreciate that, Nate. All right. So we have 2 pi. We've got our integral from 0 to 2. And we have 4 minus x times 4x minus 2x squared, right?
So, the second part of it, y2 minus y1, couldn't you switch them in it? Because that makes sense the way I thought of it, the same way. But that wouldn't be the same answer, so what's wrong with going the other way?
It would, because you would be finding the length. I mean,
So it would be.
right, it matters. 5 minus 3 is not the same as
Yeah.
3 minus 5. So it does matter that we're doing the top one minus the bottom one. Remember when we were doing this back in section 1, I said we have to subtract in the right order or we need absolute values?
So could you
We
use
definitely,
absolute
we
value?
don't really want to use absolute values in the middle of this because we're going to be distributing things.
So the rule
So
is just
we don't.
whichever one is on top.
Yeah.
Goes out. Okay.
Right, it's just, yeah, you're just subtracting from the larger value minus the smaller value. Because the larger y value is a taller height, right? It's at like, say, 3 or 3.5 or something like that, and you're subtracting the lower y value that's maybe like a 2.7 or something. Yeah. All right, we need to distribute, yes? FOIL, if you will. So this is 2 pi, still there. 0 to 2 is still here. I have 16x outside minus 8x squared minus 4x squared plus 2x cubed dx.
I feel like that's the hardest and most challenging part for me, is doing all the stupid algebra stuff.
The stupid algebra stuff, I'm sorry. All right, and then we have one of those that combines. So we have 16x minus 12x squared plus 2x cubed dx. Integral. All right, antiderivative of x, 16x, 8x squared. 12x squared,
4x.
yep, 4x cubed, and it's negative. And then 2x cubed, 1/2 x to the 4th, that's right. And we're evaluating from 4, not 4, was it 2? 2 down to 0. Okay, do I have all the pieces in there right? I think I do. All right, we're going to plug in the 2. So I have 8 times 2 squared minus 4 times 2 cubed plus 1/2 times 2 to the 4th. And what happens when I plug in 0? It's 0 because I'm working with a polynomial. All right, so what do you get when you plug all of that in?
16 pi.
It's actually 8, and then I get the 16 pi, you're right. So all of that mess is 8 multiplied by my 2 pi, which is 16 pi. All that, you get 16 pi. It is clean. It's a nice answer, right? There's no fraction involved or anything. All right. We have 10 minutes, and I want you guys to get on the board and try something. If you don't want to do the integration for it, that's okay. If you want to do the integration for it, that's okay. It's up to you and your partner, okay? But if it's all you want to do is to do the setup, I'm okay with that.